Welcome to the Deep Dive, your essential shortcut to cutting through the noise and getting straight to the most fascinating insights. In a world just overflowing with information, we're here to make sure you're truly well-informed, maybe with some surprising facts and hopefully enough humor to keep you hooked. Today, we're plunging into a topic that might sound, well, a bit unexpected for chemistry: the incredible power of mechanical force. Yeah, how sheer force can transform chemical reactions. We usually think, heat, solvents.
And a toolkit.
Exactly. But imagine making molecules react with simple brute force. So our mission for this deep dive is to unpack a really cutting-edge computational model. This model is designed to predict exactly how chemical reactions behave under these intense mechanical conditions, and we're focusing specifically on a technique called ball milling.
And the core source for our discussion today is a pretty groundbreaking article. It's titled Computational Model to Predict Reactivity Under Ball Milling Conditions. It's by Armas, Temprado, and Frutos, just published in 2025. And this paper, it proposes a brand new way, really a quantitative way, to understand and predict these mechanically driven chemical changes.
So why is this so significant for you, our listener? Well, understanding this, it opens up possibilities for incredibly sustainable manufacturing.
Greener processes.
Yeah, and for inventing entirely new materials and maybe fundamentally changing how we even approach making things chemically. Okay, let's unpack this. So to really get our heads around this, maybe we should start with the basics. What exactly is mechanochemistry?
Right. Well, in its simplest form, mechanochemistry involves chemical reactions that are kicked off or sped up by mechanical energy. Think about the energy from, say, compression or shear or friction. It's literally about pushing molecules into action. And it's kind of helpful to distinguish between two main types. First, there's what we call directed mechanochemistry. That's where forces are applied really precisely, often right down at the atomic level, to make specific things happen, like forming or breaking individual bonds. Very controlled. But our focus today is more on bulk mechanochemistry. This is the bigger picture stuff like grinding or milling. Here, the mechanical actions aren't controlled molecule by molecule, but they still induce these really powerful chemical transformations.
And the key technique in bulk mechanochemistry, the one this new model is all about, is ball milling. Can you paint a picture of that?
Sure. Imagine you're grinding solid reactants together, maybe powders. You put them in a chamber with these hard milling balls, could be steel, ceramic, and then you rotate or vibrate that chamber really vigorously. It's a high-energy environment. Constant impacts, collisions. That's what drives the chemistry. And the advantages of ball milling are, well, they're pretty significant, especially if you care about greener chemistry. One of the most fascinating things is that reactants are usually mixed as solids.
Right. No solvents.
Exactly.
Yeah.
Which means without solvents. And that dramatically reduces waste. It makes it a much more sustainable, environmentally friendly option compared to traditional chemistry done in liquids. And maybe the most exciting part, it can enhance or even completely switch reaction selectivity compared to liquid phase reactions.
Meaning it makes more of the product you actually want.
Yes, or sometimes it makes a different product altogether, one you wouldn't get using standard methods, which is, pretty cool.
That sounds like a huge benefit. So if ball milling is so great, why isn't it just everywhere? Why isn't it standard practice? What's been the holdup?
That's the crux of it. The challenge has been prediction. Computationally modeling these mechanochemical processes is incredibly difficult.
Right.
It's because the mechanical forces involved are just so diverse and complex, it's chaotic in there.
Right.
And while there were some simple theoretical ideas and even some more advanced models out there, until this work, no models really existed that could directly quantify the amount of mechanical work being done during ball milling and link that directly to how much the activation energy, that barrier the reaction needs to climb, actually changes.
And that right there, that lack of predictive power, that's where this new model comes in as a breakthrough.
Exactly. The Armas et al. Model we're digging into, it proposes a simple yet effective mechanochemical model. It's specifically designed to quantify that mechanical work and see how it affects the activation energy in ball milling reactions.
Yeah.
Its main goal is really practical, to help chemists figure out if a particular reaction is likely to be boosted or promoted by using a ball mill.
And the core concept behind it is pretty neat, isn't it? How does it simulate that chaotic environment?
It uses what they call a simple force scheme based on isotropic compression. Basically think wall-type forces.
Wall-type forces?
Yeah, imagine the molecule being squeezed between two rigid virtual walls. But And this is key. It does this simulation from all possible directions.
Ah, okay. To mimic the randomness of the ball impacts.
Precisely. It captures that random all-angles nature of the collisions in a real ball mill. And from that simulation, the model calculates the mechanical work applied to the molecule as it goes along its reaction path, from reactant to transition state. Then it predicts the change in the activation energy. And importantly, its predictions line up really well with what's seen in experiments.
So it works in practice.
It does. It confirms mechanical forces play a big role. And interestingly, it also shows these forces can affect the forward reaction differently than the reverse reaction in an equilibrium.
Okay, let's touch on how it works. Maybe without getting lost in the weeds. It needs some starting info, right?
Yeah, it starts with known molecular structures. You need the structure of the reactant, the starting molecule, and the transition state. That's the peak energy point on the way to the product.
Which you'd usually get from other calculations, like quantum chemistry.
Exactly. Then it figures out the structural change needed to get from the reactant to that transition state, ignoring overall movement or rotation.
And you mentioned something about a sphere.
Right, it sort of defines the molecular sphere around the reactive part of the molecule. This helps define where the forces are applied and in what direction. The radius is basically the distance from the center to the farthest atom, maybe with a little correction for atomic size.
Okay, so you have the sphere, the path, then the wall forces.
Yep. The model simulates those two rigid walls compressing the molecule from opposite sides for any given direction. Atoms on one side get pushed one way, atoms on the other side get pushed the opposite way.
And how much force?
The total force is based on the experimental impact pressure, what you would actually measure or estimate in the ball mill. That pressure, often huge, like gigapascals,
Gigapascals.
is applied over the molecule's cross-sectional area. Then that total force is distributed among the atoms involved. In this first version, it's distributed equally.
And then it calculates the work.
That's the core bit. It calculates the work done by these forces as the molecule follows that reaction path. That mechanical work, they call it WEMEC.
WEMEC, got it.
Directly translates into a change in the activation energy, mech. If WEMEC is positive, the barrier is lowered, the reaction speeds up.
But one direction isn't enough for the chaos of ball milling.
Absolutely not. So the model doesn't just calculate for one squeeze direction. It averages the effect over all possible directions. We're talking thousands, like maybe 20,000 different angles, to get a really robust, realistic estimate of the overall mechanical effect on that reaction barrier. And despite all that, the beauty of it is that the model is actually simple to implement and, crucially, has low computational cost.
Meaning chemists can actually use it without needing a supercomputer for weeks.
Exactly. It's a practical tool.
Okay, so theory is one thing, but does it work in practice? The researchers tested it, right? On real reactions.
They did. They tested it on several different chemical reactions to really show its predictive power. It's particularly good for making qualitative predictions, like will this work or not?
Yeah.
And for comparing different possible reactions or pathways under mechanical stress.
Let's hear about some examples.
Okay, first case study. The norbornadine quadracyclane conversion, NBG to QC. This is a unimolecular reaction, just one molecule rearranging itself. Normally, you might drive it with light, photochemically.
Okay.
What the model predicted was a really strong differential mechanical response. The forward reaction, NBD turning into QC, showed high mechanical susceptibility. Its activation energy dropped significantly by more than 1.2 kilocal per mole if you assume 2 GPa impact pressures.
So ball milling definitely helps that reaction go.
Definitely promotes it. But in stark contrast, the reverse reaction, QC turning back into NBD, showed an almost negligible mechanical response. Its activation barrier basically stayed the same.
Wow, so what does that tell us? It's not just speeding things up randomly.
Exactly. It shows that the forces in ball milling aren't just generic energy input. They can selectively favor one direction of a chemical equilibrium over the other.
Steering the chemistry.
Precisely. It's showing the intrinsic nature of how ball milling can control outcomes. Okay, next up, a series of classic Diels-Alder reactions. These involved anthracene derivatives.
Diels-Alder, that's a workhorse reaction in organic chemistry, right? Making rings.
That's the one. Two molecules combining. These specific reactions have been studied experimentally, yields varied, and other models have tried to explain the rate increases by, like, higher concentrations locally or changes in the electrical environment. What this new model found was that mechanical compression led to a modest but consistent decrease in activation energy across all these related reactions, something like minus 0.5 kilocal per mole under 1 GPa pressure.
So a boost, but maybe not a game changer for these ones. What's the insight?
The insight here is that while the mechanical force enhances the rates pretty uniformly, it doesn't change the underlying order of reactivity, the reaction that was already the fastest without mechanical help. It stayed the fastest with a mechanical boost. The relative speeds didn't change much.
Okay, interesting. But now the next one sounds like where things get really revealing about selectivity, the endo versus exo example.
Ah, yes, this is a fantastic case study. There's another Diels-Alder reaction between diphenylfulvene and malamide. Experimentally, this reaction had been studied both by ball milling and in solution, and the results were striking. Ball milling always gave a 98:2 ratio of endo versus exo products. Always. Didn't matter what temperature, didn't matter how long they milled it for.
98 to 2. Very selective.
Extremely. But in solution, the ratio changed depending on time and temperature. That suggests an equilibrium was happening in solution. The products could interconvert.
Okay, so ball milling locks in that 982 ratio. What did the model predict?
This is where it gets really impressive. The model predicted that mechanical activation significantly favors the formation of the endo product. The average activation energy change for the endo pathway was about minus 3.88 kilocal per mole,
A big drop.
a very significant drop. For the exo pathway, it was less, around minus 2.90 kilocal per mole under the same 1 GPa pressure. This strong differential effect favoring endo much more than exocal perfectly explains that high 982 selectivity seen experimentally in the ball mill.
Okay, that explains the forward reaction selectivity, but what about that equilibrium? Why doesn't it happen in the mill? What about the reverse reaction?
Good question. The researchers looked at that too. They modeled the retro-Diels-Alder reaction, specifically the endo product breaking back down, and the prediction. While the forward reaction got that big 4 kilocoulomb boost, the retro-Diels-Alder, the reverse pathway, showed an almost negligible mechanical contribution. Its activation barrier was barely affected by the simulated forces.
Ah, so for you, the listener, this is the key. The model shows that the forward reaction to make the desired endo product is strongly encouraged by the milling,
Right.
but the reverse reaction, the one that would allow it to equilibrate and maybe form more exo, isn't helped by the milling at.
Exactly. It perfectly explains why you don't see an equilibrium between endo and exo products under ball milling. The reverse path is effectively shut down, mechanochemically speaking. And just one final interesting point on this one. This particular Diels-Alder showed a larger overall mechanical effect compared to the anthracene ones we mentioned earlier.
Why was that?
It seems to be because the starting structure, the reactant adduct, is structurally more different from its transition state in this case. There's a bigger shape change happening during the reaction. And that larger structural change allows for more mechanical work to be done along the reaction path.
Makes sense. More change means more opportunity for the squeezing to help it along. Okay, so we've just taken quite a deep dive here. We've unpacked how this simple yet pretty powerful computational model can predict and explain the really fascinating world of mechanochemistry, especially in ball milling. We saw how mechanical forces aren't just brute force, they can be selective. They can promote reactions, dictate product ratios, even shut down unwanted reverse reactions.
Yeah, the significance of this model is, I think, quite high. It gives chemists a straightforward, efficient tool to screen reactions. They can quickly identify transformations that might really benefit from ball milling, pushing us towards more sustainable and accelerated ways of making molecules. And it doesn't have to be used in isolation. It can be combined with other computational methods, maybe looking at the solid-state environment effects too.
And think about the implications of this for you listening. It's not just about making chemistry, a bit greener or faster. It's potentially about fundamentally changing how we approach chemical synthesis. We're talking about steering reactions with these precise mechanical nudges instead of just relying on heat or solvents. It opens up completely new ways of thinking.
Absolutely. And because it's simple and computationally cheap, this model could be used to explore tons of new applications. Think green chemistry, new material synthesis. It really could accelerate innovation.
So here's a final thought to maybe mull over. Imagine a future where we don't just heat things up to make them react. What if we can selectively squeeze molecules into becoming exactly what we need? What other reactions, maybe ones we currently think are impossible or just not selective enough, might suddenly become not just possible, but highly controllable when we learn to apply forces in just the right way?